Hello and welcome. In this problem, we want to analyze a heat exchanger. Well, actually, this is the condenser of a power plant and steam is being cooled by circulating cooling water. So what is known about the problem is that, that the steam comes at this condition, let's call this state 1, and then exit as a saturated liquid at state 2. It is cooled by circulating water at 25 degrees Celsius. So let's say it's coming from an open lake, so pressure can be assumed to be atmospheric. And if the water temperature is not to rise above 10 degrees Celsius, so the condition given for us is that at state 4, let's call it state 4, temperature cannot exceed 10 degrees above the inlet temperature. Given that condition, determine the mass flow rate of the cooling water and rate of heat transfer from the steam to the water and the rate of entropy generation, the friction caused by heat transfer inside this system. Well, if you take the entire system, let me take a red pen. If you take the entire system as a boundary around the entire system, an open system, then you see it's an open system and it's a non-mixing system because the two flows that pass through this device do not mix. Well, more of this kind of multi-flow, non-mixing multi-flow can be found in a textbook, and also if you go to the animations module, you can take a quick primer on non-mixing multi-flow, non-mixing flow, and here the governing equations are shown how they simplify. Here essentially the mass equation is trivial, but the energy and entropy equations are shown. You can also browse other animations which explains different kind of heat exchanger. In this case, and probably it's a counterflow or doesn't matter. The data that is given, that's sufficient to analyze the system. If you go to the problem sections, and this is an example problem, so I would urge you to take it's an example from chapter 4, and it's non-mixing flow. And you can find the example as you browse down at the bottom of that section. So this is the problem we are trying to solve. And if you click on the unrestricted solution, the manual solution tab, then you will find the manual solution of this problem. So please go through this before you try to follow the test solution. So what test step do we need to solve this problem? Obviously, we go to the test steps page and system analysis. It's an open system, open steady system. So if you go down this tree, open steady system, it's a generic system, and here is non-mixing multi-flow systems, which heat exchanger is a great example of that. If we click there, you will find the PC model. That should be our model of choice. Why? Because we have steam passing through. One of the streams is made of steam, a saturated mixture going to saturated liquid. Another stream is water, which also we can model with PC model. So this is great. So I have already launched the PC model and already filled out some of the data given to us. So let's go over this. So state 1, the inlet state, the pressure is given 15 kPa and the quality is given, even the mass flow rate is given. So the state is totally known. Let's go to state 2, the exit state. So obviously the mass flow rate doesn't change, the same flow going out. Pressure doesn't change. There's no friction we'll assume in the condenser. And the quality at the exit is 0, that is a saturated liquid. Remember, state 1 is steam coming here, and state 2 is the exit where it became turned into condensed water, saturated liquid water. Okay, What about state 3? So state 3, let me erase that. For state 3, what we know is that the pressure should be assumed to be 1 atmosphere. So let's put 1 atmosphere and calculate. So we find the state of state 3. Note that the mass flow rate is an unknown, temperature is known. We'll leave it there like this. And state 4, the mass flow rate will be same as state 3. And the pressure will be same as P3. And what about the temperature? The temperature, we are writing as, the temperature will be T3 plus, remember, 10 degrees Celsius. It shouldn't exist. We can write T3 plus 10, or in preparation for a parametric study, we can introduce a variable, delta T, or in Celsius. Whereas if I now calculate, obviously both this cannot be determined. T4 cannot be determined because we don't know what delta TC mean. We also don't have any info on m.3. That's why they're white background. But this is a user-defined variable. So we can go to the I/O panel and we can introduce some user code by clicking the isolate user codes button and then clicking here and defining the variable delta T in Celsius equals 10. So now if I click a calculator in the I/O panel, what happens is that this variable is registered and delta T in Celsius is recorded as 10. Doesn't matter, you can name it any variable. Generally what I do, I put the name of the variable first and the unit second. That's how I compose variable names. If you now go back to the state panel, and now that delta C is known, if you do another calculate, you'll notice this is a green background now, so T4 can be evaluated. And oh sure, you can just point your mouse over T4 and you can see the value will appear in this zone. So keep an eye over this space, and when I move my mouse over T4, you can see its value shows up. That's how you see value of any given variable if it's in terms of a variable. So T4 is 35 degrees Celsius, which is correct. So now that we have inputted everything that we know about this problem, let's set up the device. What we know about the device is that state 1 and state 2 constitute one of the flows. This is the steam going through the system. And state 3, well, the way I drew the diagram, it would be nicer. Let's put this as water. State 3 going, the circulating water, and the steam going from 1 to 2. Doesn't matter, you can choose either way, the result's not going to change. Notice that the governing equations are shown here, and because the heat exchanger is insulated, Q dot is 0, and there is of course no work, so that simplifies the solution. So what we do now is that let's enter Q dot equals 0, W dot equals 0, and do a calculate and do a super calculate. Hopefully that should solve the problem. So now we go back and take a look. Yes, if you notice, state 3 mass flow rate has been found. State 4 is of course m.4 will be equal m.3, and in the device panel you can see that the entropy generation has been calculated here. So all the answers have been found. If you go to the if you go back to the solution page, you can quickly check. Notice the answer to the problem of how much C is what? The rate of entropy generation is 3.6 kilowatt per Kelvin, and you can come back to our solution and see, take a look, and it is 3.6 kilowatt per Kelvin. So we got the correct answer. Now to do a what if scenario, for instance, again, no, before what if scenario, let's isolate the code. And remember, they also asked what is the heat transfer from the steam to the water. That we can introduce a variable called q dot steam to water in kilowatt. It would be what? M dot 1, remember that's the mass flow rate of the steam, and it brings in flow energy J1, and it lives with flow energy J2, specific flow energy. So this should be the heat transfer we are looking for. If you click a calculate, you can see the heat transfer has been calculated here. Obviously, this must be the same as, just to double check, q dot gain by water, for a lack of better terminology, q dot gain by water is what? Kilowatt. That's m dot 2 star J4 minus J3. See if it makes sense to you. J4 is the exit state, J3 is the inlet state of the liquid water that is circulating. So the heat gained should be that much, and we know heat lost by the steam should be exactly equal to heat gained by water, because the heat exchanger is insulated. So let's see if we are correct. If you're correct, we made a mistake somewhere here. Okay, so what's wrong? Why these two values are not equal? I must have made a mistake. So q dot steam to water, that's correct. M dot 1 J1 minus J2. Oh, here we go. Take a look. For heat gained by water, it's not M dot 2. It should be M dot 3 or M dot 4. I bet now the two numbers will be equal. If I click a calculate button, you can see exactly they're equal. Of course, you can do a super calculate to get all your results together, which will first give you the test codes that has been generated, and then your own code, which we call the user codes, delta TC being the parameter. So for instance, another question was, how will the answer change if delta C is different, delta TC is different? You can just modify that here, or better, you can isolate the user codes that get rid of all the other test codes. And the question is that, what if this is 5 degree? So if you click just 5 here, replace 10 with 5, and then first calculate to register your change. So delta C is now 5, and do a super calculate, and you're done with the what if scenario. Now if you go back in the device panel, you will find the entropy generation that you see. This will be slightly less than before, because now the temperature difference between the two streams is a little bit less, and therefore the thermal friction will be less. Just to verify that we got the right numbers, you can go back to state panel and make sure that state 4, the temperature difference is 5 degrees, so it should be 25 plus 5, 30 degree, which shows up here as 30 degree, as you can see. Another thing to check could be go to the graphics panel and just look at the states to see if they make sense, and you can draw the constant pressure lines, and you realize there should be two different pressure lines, which in this case is almost invisible. They're going through state 1 and there is state 3. If you do another pressure line, so these are the two different pressure lines. One is the pressure of the steam at 15 kPa, another is pressure of liquid water, both of which are condensed, subcooled liquid water. That's why they're showing like this. Okay, we are done.